Well, guys, I made it. You know, they say you always remember your first trolley comment on a random educational video you make for your students during a global pandemic. So let's talk about it. I'm gonna not read the whole thing because the whole thing doesn't matter, but if you do want to read the whole thing, it's on my conservation of angular momentum scenarios video. There are some things in this comment that I just want to talk about because I just want to make sure that you're clear that the physics that I presented in the video is correct. So the start of the comment says, the problem with your demonstration is that it does not conserve angular momentum. The reason that it does not conserve angular momentum is because angular momentum is not conserved. Not true. Angular momentum is most certainly conserved. It says, measure your demonstration, or ice skater. I believe they're talking about where I spun in my chair and brought my arms in and stuff like that. And you will find that the spin faster because they're conserving angular energy. Angular momentum is not conserved. And then it goes through this whole thing accusing me of XYZ. You can read the whole thing on your own. Anyways, I just wanted to kind of approach what they're talking about and give some physics behind why what they said is not true. So, first of all, we have to start with this idea that angular momentum before equals angular momentum after. We know this is absolutely true. Okay? It is the reason that we spin on our axis, because as all the particles that make up our planet were swirling around, that spin was remembered due to the conservation of angular momentum. We know the reason we orbit the sun and the way the other planets orbit the sun in that same direction is due to the conservation of angular momentum. All those particles and rocks and stuff that ended up making these planets were all orbiting in the same direction. So when they clumped together to make the planet, that momentum was conserved. It's absolutely conserved. Now, if you talk about I've realized I just wrote something on my board, didn't show you. Not a big deal. Anyways, if you go back to our demonstration where I was the ice skater spinning around, okay, we say that before equals after, right? Let's rewrote what I just erased. Before to after. Right? So angular momentum before equals angular momentum after. Remember that angular momentum equals rotational inertia times angular velocity. Okay, so the rotational inertia before times the angular velocity before equals the rotational inertia after times the angular velocity after. Okay, by doing that, by bringing my arms in, I lowered my angular momentum. Now, I lowered my rotational inertia, increased my angular velocity to keep that momentum the same. There was no outside force to spin me faster. Right? I just brought my arms in, momentum was conserved. Now, let's talk about rotational energy, because that was another thing that was talked about here, right? So remember, rotational kinetic energy is that 1/2 I omega squared. Okay? So let's talk about both of these things, rotational kinetic energy and angular momentum for that problem. And to do that, I'm going to make up some numbers. Okay? So we'll say beforehand, the rotational inertia where my arms are out, we'll just make up a number. Let's go with 2. 2 kilograms times meters squared. Okay. Then we'll say that my rotational or angular velocity for that first thing, let's make up a number and say it was 5 radians per second. Okay. Now let's go with after I brought my arms in. Okay, let's say by doing that, by bringing my arms in, I have cut my angular or my rotational inertia in half. Oops, sorry, wrong symbol. Okay, so before, rotational inertia, 2 kilogram meters squared, angular velocity, 5 radians per second. Afterwards, rotational inertia is 1 kilogram meter per second squared because I cut it in half by bringing my arms in. And we're going to find the angular velocity afterwards. Now, we're going to use the conservation of angular momentum to help us solve this problem. So we'll say I omega equals I omega. Okay, 2 kilogram meter squared times 5 radians per second equals 1 kilogram meter squared times an unknown omega. Okay, well, we'll see that this is 10 kilogram meter squared per second equals 1 kilogram meter squared times omega. Solve for omega, we get 10 radians per second. Okay, so by cutting my rotational inertia in half, I've then doubled my angular velocity, which matches. Now, let's use these same numbers to see if rotational energy is conserved, because that's what they said in the video, that the rotational energy is conserved, okay? Drop my marker. So much fun. Okay, so the idea is that the rotational energy beforehand should equal the rotational energy after. Okay, so 1/2 I omega squared for before may or may not equal 1/2 I omega squared for after. Okay, let's plug stuff in. Well, we know the 1/2 will cancel, so I'll plug in. So before we said our rotational inertia was 2 kilogram meters squared, and beforehand our angular velocity was 5 radians per second, don't forget to square it, equals our new one, which is our new rotational inertia, which we said was 1, cut it in half, times our new rotational or angular velocity, which we calculated just prior, which is 10 kilogram meters second squared. Sorry, 10 radians per second. Don't forget to square it. Now, we've got 2 times 5 squared. 5 squared is 25, times 2 is 50 kilogram meters squared per second. 1 times 10 squared. 10 squared is 100, times 1 is 100. These are not equal. In that scenario, rotational energy was not conserved. Okay? Angular velocity is conserved in a closed system where there's no outside torque. Me spinning around or an ice skater, there is no outside torque. Okay? So angular momentum is conserved. Angular energy, rotational energy, is only conserved if it occurs in an elastic collision. Okay? Since there was no collision there, that rotational energy is not conserved, as you can see from the math. So I just wanted to bring that up, and we'll see what goes from there. Have a good one.